welcome to today's event, where we're going to be taking a look at mixed signal and how we can work with FPGAs and ADCs and DACs. This is the final part of four webinars that we've been running, and hopefully it's going to take us about an hour to run through. If somebody could just quickly pop in the chat and let me know if the sound and the video and everything is okay. I had a real nightmare just setting up for this. I had to restart my laptop like literally 2 minutes before the before we started. So I was like, "Oh, am I going to be here? Am I going to be late?" But it's going to be, hopefully, it's going to be a good session today. We've got some demos. Hopefully, we're going to take a look at some of those as well. First off, we're going to start running through a few slides and things like normal. And as I say, as we go through, please ask any questions as we go through and raise them as we go along. So let's make a start on this. And it's interesting really because FPGAs, you know, they're great for working with signal processing, image processing, and things like that. But one of the key things we have to be able to do is we have to be able to understand how to work with those analog to digital converters and digital to analog converters that we might want to use in our FPGAs. So today we're going to take a look through some of these concepts. Like I say, it's going to take about an hour. As we get any questions, please pop questions in the chat. Everything we do, I will be releasing on a GitHub later on today. So if you go back to my website after this, you'll be able to find a recording of this session, links to the slides that we've presented, and links to most of the projects that we're going to be talking about. There is a project that I'm going to use as part of the demonstration that will be made available by my Hackster, but that will be probably in a week or so's time that pops out on there. So without further ado, let's take a start. So when it comes to it, really, you know, the world is analog. You know, the world is a continuous system. You know, our sight is continuous, our hearing is continuous. You know, how we interpret everything, it's a continuous signal, not a discrete signal, like we need to process digitally. Unfortunately, you know, those signals, they do get subjected to noise, to distortion easily. So actually, in a lot of cases, the best processing that we can do, the easiest processing we can do, is to process it digitally. And it's actually relatively simple to do that conversion, as you'll see. As we're looking at today, and our FPGAs, they give us a really great implementation to be able to do this, because actually when we have this parallel logic, this programmable logic, the block RAMs, the DSPs, we can easily implement filters, processing, whatever we want really in there to do that processing. And application. And hopefully some of the other classes that we've talked about previously, you know, the how to write VHDL good, how to get timing performance, and how to do maths in FPGAs, you know, they all come together and help us be able to leverage and work with these ADCs and DACs. So our objective for today is to take a look at some common mixed signal applications. We always tend to think about sort of image processing, radar processing, signal processing, but there are some really interesting examples as we'll see as we go through. We're going to take a look at what is the basics of an ADC and DAC, and how we can pick ADCs and DACs to give us the best performance, the best quantization. For working with our FPGAs, and then we're going to take a look at sort of, you know, the Nyquist rules, how we can sample in signals, the aliasing, and then we're going to take a look at some real world examples. So we're going to leverage the XADC, the system monitor that's provided in most AMD FPGAs. Obviously, it's not in the absolute tiniest of tiniest Spartan 7 devices. But it is in others. So we're going to take a look at an industrial application that I've got down on the bench here. I'll just flip it down there. We've got a couple of boards on the bench. We've got an RT S7 and one of our Leonidas boards that are currently running examples on it. So we'll take a look at how to do that. And we're going to take a look at, like I say, how to create an example using the XADC. We're going to take a look at how to create a delta sigma DAC in the in a Spartan 7, and we'll take a look at how to do that with a PWM as well, because that's kind of interesting, and it gives us a point to look at and compare between the two of them. So if we think about like I say, the world's best processed is analog and best processed digitally. So there are several things where we might want to use an analog to digital converter. For example, like I'm doing now, we need a microphone to convert the acoustic energy that coming from my voice into a voltage that can then be sampled and shared with you all on this recording. We might want to be looking at an industrial application where we have strain gauges, for example, to understand how much stress or strain is being placed on something. Or, as we'll see in the demo today, the temperature side of things, where we want to measure a temperature. So when we come to look at our ADC application later on, we're going to be using a negative temperature coefficient thermistor with a little RC network, and we're going to use that and the XADC to actually convert the resistance that's measured, actually the ADC count that's measured, and convert that into go through a processing chain to convert that into a temperature. Obviously, you know, we can use them for telemetry as well to measure our voltages and currents, and that's really simple with those XADCs, because we can just read that data directly. It's available to us directly over the AXI bus or the DRP bus. We also might want to do some communications. You know, wireless communications is key for a lot of this. So we might want to use RF energy. We might want to do some receive in some RF signals, you know, some I and Q, sum and phase sort of data, and do some demodulation and conversion of it. Today we're not going to talk too much about that, but these are kind of a wide range of applications that we use these analog to digital converters for. Similarly, you know, with the digital to analog converters for audio playback, you know, they're converting my ramblings to a acoustic signal that you can hear. Similarly for telecommunications, you know, for wired and wireless communication, and for instrumentation as well. If we want to convert voltages or currents to actually control actuators or drives, or do some robotics, like on the robotics arms on the shelves behind me, then they can be quite useful. And obviously, if we're doing things like communication or radar, then that generation of the waveforms can also be very important. So let's take a look now at the basics of an ADC and DAC and see how we can understand a little bit about these. So the ADC, you know, that's the first bit, and its role is to convert a continually changing analog voltage or analog signal actually into a quantized digital value. It does this by using a sample and hold circuit that samples on the clock signal that we give it. Once we've got that clock signal and we've got that sampled value, it then does an A to D conversion. So it converts the analog value to a digital value represented by 8, 12, 14, 16 bits. However, how it can do that A to D conversion, it varies depending upon the technology of the ADC that's being implemented. You know, we might use a flash converter because obviously we want speed if we're using a flash converter. So that will use several analog comparators to against the input voltage and reference voltages to actually work out what the digital code is. We might use ramp converters, you know, which use free running counters to go there and compare against the input voltages until the count is actually determined. Or we might use quite a common approach actually for low speed ADCs and DACs, is we might use a successive approximation approach to do that analog to digital conversion. The key thing is we're going to put in an analog voltage and we're going to receive a quantized digital signal out of this that's going to be several bits wide for each sample. Once we've got this, obviously, it gives us a lot of immunity to noise. It makes it easier for processing because we're not worrying about drift or temperature tolerance or aging or anything like that. It's just purely in the digital domain. There's a couple of things we might want to think about though when we're doing an ADC conversion. You know, we follow the standard sort of y equals mx plus c, and I think this is one of the first webinars I've given where I've got lots of equations in it. So I'll apologise. I'll apologise in advance. But for a digital output, we need the analog input. We need the number of digital codes which can occur for a change in an analog input, and we need the minimum output value that's applied when you get the lowest voltage applied. Unfortunately, however, ADCs they're not entirely perfect devices. So we can see offset errors that might be applied into them. And keep this in mind and try and remember this. There's not going to be a test at the end of it, but when we look at the example for the XADC, this is quite interesting. So we could see an offset error where we have where we get a non-zero result for a zero input, or we could see a gain error which gives us the scaled result is different to what we would expect it to be because there's some sort of gain within the system. Now, what we can do is we can calibrate these out, and we'll see when we look at the XADC that we can do some calibration of the ADC to correct for these. So in this instance, C contributes the offset error, and M is an example of the gain error that we can see. We can also see with ADCs, we expect them to have a nice linear step for voltages. They have a minimum voltage resolution, minimum step resolution, and we expect them to ideally to increment with 1 LSB code widths. But what we might see with some ADCs or some implementations is we might see some differential nonlinearity, and that means where the code changes with more than a 1 LSB width. So, for example, it might be that we see a missing code, as shown there, or we might see that we see an increased code width, which covers a wider range. This, when we come to looking at the performance of the ADCs and DACs, this can result in having noise or additional sort of spurious signals or spurs, which can come into play. So we want to make sure that we minimize these. Typically, the ADC and DAC data sheets are really good at defining what these parameters are. We might experience as well some integral nonlinearity. So that's where the code transition point varies, and it doesn't change at the same point. So as you can see on the graph here, where we would expect the code to be changing is actually not the point it changes. We would expect it to be following this straight line graph, but actually the code changes at an analog voltage before we expect it to. So this will give us some harmonics and some spurious signals when we plot the spectrum at the end. So these are very important things to consider and look at, because for some applications we don't care. So for example, the XADC application I'm going to show you today, where we're measuring temperature, we probably don't care. When I was doing sort of satellite communications and such like, you would really care about spurious harmonics and spurious signals occurring within the communications channel, because it reduces your link budget and your link performance and has a knock-on effect. So we want to make sure that we're working in the best way that we can. So having had a quick introduction to ADCs, we can do a similar thing with digital to analog converters, and in this case we're going to be putting a input vector, 8, 12, 14, 16 bits into a latch. We're going to be clocking that, and then we're going to be using a reference voltage to scale the output analog signal that we want, and we may generate that digital output in several ways. So we might use a binary weighted network to generate the output. We might use an R to R ladder, or as we'll see today in our examples, we might use a PWM to reconstitute the analog signal, or even a delta sigma or sigma delta, depending on how people pronounce it, to actually generate that output signal. And we'll be demonstrating this in a little while, and the projects for the PWM and the delta sigma will be available at the end of this session. Just like with the ADC, we have the similar equations and similar outputs for the DAC. So again, it follows the y equals mx plus c type structure. Oh, again, we can see an offset errors, and we can see gain errors again. Nothing too complicated really about this. What we can see as well with the DAC is we may see some differential nonlinearity, and again, similar to the ADC, where that's where we don't have 1 LSBs of steps in between the two, or some integral nonlinearity also. And what these are going to do is, again, similar to the ADCs and DACs, similar to the ADCs, where we see spurs and harmonics being created on the data that we've captured. So the quantized data, which appears in our processing chain, this is going to put spurs and noise on the output of our signal processing, in addition to what we've already captured from the analog to digital, or from what our mathematics in the processing chain has added into the system. So we can have a lot of fun reading data sheets and trying to work all this out. But there are some key parameters when it comes to selecting the right ADC and DAC. Just like selecting the right FPGA, we have to spend a little bit of time and think about this a little carefully. So a couple of the parameters that we might want to consider are the signal to noise ratio, and that represents essentially the quantization noise that we would see in the ADC or the DAC. We might also see, and there's a diagram coming up, the spurious-free dynamic range, and that's the ratio between the highest input signal and the highest peak, which is occurring within the output spectrum. That could be a harmonic of the fundamental normally, or if we're really unlucky, it could be some noise or some artifact that we've managed to generate in our design somewhere. One of the more interesting elements as well is we can actually calculate the effective number of bits that the ADC or DAC is giving us. So for example, if we have a 12-bit ADC or a 12-bit DAC, it's very unlikely that all 12 bits of those are actually effective in our system. And using the signal to noise ratio and the spurious-free dynamic range, we can actually calculate what the theoretical effective number of bits is, and what the real measured effective number of bits is. And when I get some time, it's one of the things I actually intend to do is create quite a detailed Haxer project around a couple of ADC boards that I have with the FPGA to show how to actually go about properly characterizing and calculating the effective number of bits and the signal to noise ratio. As I said, theoretically, we can calculate the signal to noise ratio depending upon this equation here, which shows the number of bits that we have in our design. Obviously, that's the theoretical side of things. It all comes down to what we put in the reality, what we put in our design. And it's much more than what ADC or DAC we select, or even what we do in our FPGA. A lot of this also comes down to PCB layout, power integrity, signal integrity, things way beyond the scope of this talk. But it's not unusual to use the FPGA or to put a design in the FPGA when you're bringing up or designing these boards to actually capture this data to allow you to work out what is actually going off in your system, and whether you have issues or not, or whether you're meeting your requirements or not. So if we were to plot this, what we can see is that we can, using the spurious-free dynamic range, so between either the full scale and the worst spur, or the input signal, the carrier signal, we can work out the effective number of bits that we see within our system. All very important and all very useful when it comes to quantifying our designs, explaining how well our system works, and of course mapping it back to some requirements somewhere in our system that says our RF, our analog, our digital interfaces will comply with these standards. One of the cool things we can do, and one of the reasons why FPGAs get used so much in this application actually, is we can use the FPGA to capture data, or we can use the FPGA to if we capture it if we're using an ADC or DAC. An ADC, if we're using a DAC, we can use it to generate waveforms that can be output and captured on a spectrum analyzer to do the same thing. But we want to be able to capture the signal coming in, take an FFT, calculate things such as the signal to noise ratio, the spurious free dynamic range, the total harmonic distortion, and obviously work out where the noise floor is. One of the key things that we're doing when we're calculating this, if you ever have to do this, is you need to take into account you really do need to take into account the FFT noise floor and make sure that it's well below what you're actually going to be looking for, depending upon the characteristics of the ADC or the DAC. Hopefully everybody's still awake. This is probably one of the more technical things that we've talked about so far in these. But this is really what we want to do. So we know that we can capture signals we can convert from analog signals using an ADC, we can convert to digital using a DAC, so from digital to analog using a DAC, and we know that there's a number of parameters such as SFDR, effective number of bits, signal to noise ratio, that help us understand the performance of our system. Now, one of the things that we really want to do is to be able to use these ADCs and DACs to transfer data. And that's really what we use it in a lot of applications. We're using them to transfer data or to receive data, do some processing on it, and then transmit on it somewhere else. And being able to capture data without losing it is critical. So this is where we have some Nyquist-Shannon sampling frequency theorem comes into play. And what this says is that a continuous signal can be completely represented in its sample and perfectly reconstructed if it is sampled at a frequency that is at least twice the highest frequency component of the signal. And that's an interesting point, because the highest frequency component of the signal might not be the frequency that is not just necessarily the carrier signal, because obviously that might be different, because there will be harmonics and frequency content in it. But generally, by and large, when we want to sample a signal, our rule of thumb as engineers is we need to sample it at least twice as fast as that. So if we have a 1 kilohertz signal, we need to sample it at 2 kilohertz. We get more information if we oversample. We can get a better quality if we oversample it, but we at least need to sample it at twice the frequency. And what this means, though, is if we sample differently to this, we can actually make signals that are higher that are outside that criteria come back and alias back into the signal to be able to be actually accessed and done. So it acts as a kind of a down conversion without having to do any down conversion. So, for example, we break this up into Nyquist zones. So if we have the sampling frequency at the center point here, then within the first Nyquist zone is anything that we're between that and half the sampling frequency. We can capture anything, and capture anything is not the right word. We're using the traditional approach there, where we're oversampling at least twice the frequency in the first Nyquist zone, because the signal is lower than that. As we move into the second, third, and fourth Nyquist zones, obviously the frequency is higher, but what happens is we can capture that data will alias back into the sampling input of the ADC, such that we can then sample it. So if we have a signal here, for example, FA, which is outside that, it will alias back into the sample band, such that we can receive it, provided that our ADC has a wide enough analog front full bandwidth input to be able to capture it and process it. So what this means is that we can sample frequencies we can sample frequencies that are higher into our ADCs and DACs, and recover the signal and work with it. And you see this a lot on things such as really high-end ADCs and DACs, in that they will be designed to work across not just the first Nyquist zone, but all of the 4 Nyquist zones, to make sure that you get that full bandwidth, input, and be able to capture all the data. Hopefully that makes sense to everybody so far. So what we're going to talk about now, having taken a little look at all of the FPGA of the concept, the concepts behind all this, we're going to take a look now at the XADC and the system monitor. They're all available, all provided in pretty much all of the AMD devices. The smaller one of the 7 series doesn't have them, but by and large they're across everything. So we see in the XADC we can sample at 1 megasample per second. In the Sys monitor it's a slightly lower frequency of 200 kilosamples per second. They're either 10 or 12 bits. What's really nice though is they can be either unipolar or bipolar inputs, and we can use these to sample between either 0 and 1 volts or plus minus half a volt. Along with monitoring externally, we can also monitor all of the internal supply voltage rails and temperatures, and we can monitor up to 17 external signals using the dedicated VP-VM pair and the auxiliary pins. And even if we just want to do something with the VP-VM pair, we can use it to drive external multiplexers to do the sequencing. And it has some really nice features, such as there's an internal sequencer in there that we can put in there. We can do averaging of signals, and it's also got automatic gain control and offset correction. So if you remember back to when I was talking about ADCs and DACs, and I was talking about the offset and the gain, then the ADC XADC is able to help us do that. We can drop it in our design really simply by adding in either the XADC wizard or the Sysmon wizard, and we can really use the GUI to help us drive and configure this if you're not familiar with it before. One of the nice things is we can make it output either just either an AXI stream or just a stream of a vector of conversion samples that are going to come out of the back of it, so we can take it and work with it. It's very useful. Not only is it useful for doing some of those applications that we wanted to talk about, such as industrial things or even communications, but it'd be very slow. But it's very useful if we want to do things like built-in test or security monitoring, because we can look at make sure that our voltages and temperatures and such like are within acceptable limits. And if they're not, then we could say, hey, somebody's trying to do something with us, so let's have some sort of response, an anti-tamper response, or something like that. One of the nice things about working with this, and we'll open up Vivado in a second, is you can have so much fun with it. So you can put a simple little XADC here. You can connect it to the VP-VN, and this is actually a Hackster project that you can see on my Hackster, where we put a light-dependent resistor going into the VP-VN. We then had a little servo drive coming out of the back that was generating a PWM waveform. And we got it to play the Google Chrome jumping dinosaur game, which was a lot of fun to do. But it shows just how simply you can use the XADC to run through that. So let's take a look now at a little example of this. Hopefully, my project will have loaded up. While people think about it, they can put any questions in the chat, or they can tell me where I got something wrong as I was explaining the earlier bits, and we'll go through that. While we do that, I will also open VS Code, and we should be in a pretty good position. Always takes a little bit longer to open up when I start opening up the projects. Yeah, Martin, that's a great explanation, actually. So we can pull that through into here. Once it's finished updating, we can take a look at it. So the system monitor and the XADC, they're slightly different versions. One's put in the ultrascale, the system monitor's put in the ultrascale and the ultrascale plus. The XADC is in 7 series. You have to actually, over the hardware manager, if you just connect over the hardware manager, you can see the temperature. In fact, actually, I'll connect to the hardware manager in this one in a second. I'll show you the block diagram. And then I will show Venkat. I will show that. So this example, this is going to be a HACSA project in a couple of weeks. It's just going through approval at the moment. But what we have here is the XADC, the VPVN going off board. That goes out to a little, I've turned my camera down, maybe you can see it. That goes out down to this little Veriboard type thing down there that's got a resistive network on it and a negative temperature coefficient thermistor that gives us a value that comes in through the XADC. The XADC gives out a 16-bit value for every conversion, but it's not the 60. But actually, it's only a 12-bit output. So we use a subset converter to just snip off the bits that we want and to put the bits into the right instance. And then we'll, as you'll see in the HACSA project coming up, we put it through an IP core to do the conversion back to temperature. The XADC itself, once it finishes running through this, we can configure quite in a wide range of ways. So if we want a user interface on it that comes in over AXI4, we can do that, or the dynamic reconfiguration port. Or generally, in this case, I didn't want to do that. I just wanted to configure it. We can set the AXI stream. We can set the continuous mode. We can allow it to. We can tell it to do the gain and offset calibration. I also set it to do channel averaging here because it's not receiving a communication signal. It's receiving an ADC, a more or less a stable voltage level. I turned off all the alarms. I set the single channel, so the sequencer in the ADC is just set to do one single conversion all the time of what's coming in on the VPVN channels. If we then go back and open, and apologies, I did have all this open right up until the point my computer crashed just 2 minutes before the webinar was due to start. I click on that, yeah, it's running. While that opens up, I'll show you, Venkat, this in the hardware manager. If we open the target, hopefully this will connect to a Spartan S7 board. If it connects to a Digilant analog devices, we'll be in. You can look at that. You can see both. Might have to unplug one of these actually in a second. What's that doing? While that's doing that, we will open the workspace for that. Have a look at the questions. What have we got on the questions? So yeah, so does the R6A7 have an XADC? Yes, it does have a yes, it does have an XADC in there. It's only the smallest ones of the 7 series that don't. Let's just disconnect that. That looks a bit odd. I think something's gone a little awry there because it's running yeah, it's very odd. Very weird, that one. Let's try that in a different one. See if it wants to connect. There's the demonstration of a live demo. I think what might have thrown it is I've got an analog discovery connected as well to generate some waveforms, but it doesn't seem to want to play. We'll come back to this in a little while. Otherwise, we'll never get anything. Anything done. I'll come back to that at the end with a demo before we wrap up. Otherwise, we'll not get through it all. Apologies about that. So one of the things we want to do, we might want to do with our systems, obviously, is generate the data going back out of it. And in this example, I'm going to show you 2 examples. I'm going to show you a PWM, and I'm going to show you a delta sigma DAC. PWM is honestly, it's the simplest way to do it. We're just going to regenerate a simple sine wave at 1 kilohertz. How we do it is, we have the duty cycle that's going for the PWM signal, and we can chunk that up into a number of periods. We can adjust the width on it such that when we put it through a RC filter, we recover an analog signal coming back out of it. The PWM signal's got 2 key elements, obviously: the period, which is how often the repetition of the signal, and then the duty cycle, which is how much of the period is actually turned on. What we did to recreate the sine wave using a PWM is we actually broke this down. So we plotted the sine wave, as you can see. We asked the sine wave. We then chunked this up into 12 separate different elements. So it's 12 discrete points. So the 50%, the 75%, the 93, the 100, the 93, the 75, the 50, the 25, the 7, the 0, the 7 again, the 25, and the 50% again. So we broke that up into these 12 segments, and each one of these 12 segments equates to essentially 30 degrees of the sine wave. So every 30 degrees, we were taking a sample point from it. I wanted to generate this at 1 kilohertz. I wanted a 1 kilohertz sine wave. And to do that, obviously, we've got 12 bits of it, so we have to go 12 times faster. So that's what we did. We segmented this into 12 times. We generated a PWM frequency to run at 12 kilohertz, which is basically a period of 83 microseconds. And then it just ran through and counts through and runs through. And we can see this quite easily on the hardware. And I will make this code available. Let's take a look at that. That's actually running. It doesn't need Vivado to run. We just need waveforms to do this one. So if we start running this, I'll maximize this. Look at that. I'm going to turn channel 1 off for the time being, and we've got channel 2, and I'm going to increase the voltage step a little bit, and then we should actually change the triggering such that it's running on a normal trigger, and we'll trigger on channel 2 because we're on channel 2, and we'll change our trigger. So we can see we have a rudimentary sine wave coming out. It was actually a lot more difficult to get the PWM to give us a nice sine wave than it was the delta sigma, as you will see in a minute. So this has actually got a two-stage RC filter on the output, not a single stage RC filter. And if we do an FFT of this, we certainly don't want a span of megahertz. If we do an FFT of this, this all set up nicely earlier on. But we can basically see we have a peak here. So if we go with a Hamming one again, we basically have a signal here at 1 kilohertz that we can see. But we have a lot of spurious sort of noises and spurs coming from this, because if you look at the waveform, it's not exactly the nicest waveform there is going on here. So it creates us a little bit of an issue. If we make that a little bit larger, and maybe we take the span out a little bit to sort of 20 kilohertz, we can see that we've got a 1 kilohertz fundamental here, but we've got lots of harmonics, particularly as we go up the path, which is not too great, really. Now, by and large, the other approach to doing a analog to digital conversion is to do a delta sigma. Is to do a delta sigma DAC. And in this instance, this is just, again, it's a single bit conversion that we're doing, and it's really doing a massive oversampling of the input. And a simple first order delta sigma works by ensuring that the average output level represents the average input level, and it's going to generate what's called not a PWM signal, but a pulse proportional modulation output signal. And what we did next was to create a 16-bit delta sigma. So we'd be putting in a 16-bit input here. And then we do an addition, the register, we strip off the most significant bit as the output bit that goes out. And then we just feed that back and do a difference back into the equation. I'll show you this in Vivado in a second. If we go back to the demo and I turn on channel 1, I'll turn off channel 2, we turn on channel 1. What we'll see is the output from the delta sigma. Let's set that to trigger on channel 1 now. We can see on channel 1 we have a lot nicer. We have a lot nicer sine wave coming out. It's a lot cleaner, not as many glitches or anything. And we also have a lot smoother spectrum coming out the back end of this. So we've got our 1 kilohertz tone here. And if we extend this out, say if we go to 50 or to even to 100, we can see that we don't really, unlike with the, if we turn channel 2 on, you can see just how bad it is. Unlike with the PWM, where we have a lot of harmonics coming through it, and we'd need a lot more filtering. With the delta sigma, we get a lot nicer, smoother output, which works really nicely. Also, so is the theory. Anyway, what we'll do is I'll put the code back on Vivado, on GitHub. So if anybody wants to take a look at it, they can take a look at it, download it, play with it, and experiment to your heart's content. Running this through the delta sigma on the Spartan 7 board, it's minimal. You know, it's absolutely minimal. A couple of 50 or so lookup tables, 100 or so flip flops. We have it implemented in our Leonidas board, which is connected to a PMOD breakout with the filters on it, and that's got 6,000. That FPGA is the smallest of the Spartan 7, so it has just 6,000 logic resources in there. So it's a tiny bit, but it still implements quite nicely in there. When it comes to designing, in fact, you can see it there. There it is on the board. When it comes to designing the filter, obviously we need to think a little bit about what we want to do with the low pass filter. The easiest way to reconstitute the signal for the PWM or the delta sigma is to use an RC filter. And to do that, we need to work out what the correct cutoff frequency is. And that's basically, the cutoff frequency is the bit above the frequency spectrum above where we wish to begin to attenuate the signal. And the equation for a simple RC filter is, of course, 1 over 2 pi RC is going to give us the cutoff frequency. So I decided, because we were going to pass through a 1 kilohertz, we were outputting a 1 kilohertz signal. I figured anything above 2 kilohertz we would want to begin to attenuate to keep in line with the sampling frequency and such like. So I selected a 100 nanofarad capacitor and a 820 20 ohm resistor. When you calculate that through, that's just NFC just below the 2K, but that's more than enough. So that's just to do a simple RC filter for the PWM and the delta sigma. As I said, actually, I ended up, I don't know if I put the slides in here, but we can see the delta sigma output here. Looks nice, although I've connected it to different channels. It's nice and sinusoidal. The frequency spectrum is very nice there. We can see a very nice 1 kilohertz tone. Few glitches, but nothing too bad. The PWM signal, obviously, this is actually pretty noisy particularly down the bottom. It's not too great. So I needed a second order RC filter. So not only the first a simple RC, but after the first RC, another RC to try and reduce some of those harmonics. In reality, I think I would have gone for some sort of active filter if I was actually trying to do it. Or actually, to be honest, I would have gone for a delta sigma type approach. And as you can see, that's got a lot. That was, as we saw in the live demo, that was a lot more noisy than it appeared to be on the frequency spectrum, particularly as we went up in frequency. So we can see there just a quick comparison of the over 2 as we saw in the live demo, what the difference is between the two. So working with mixed signal devices, just to wrap up, and then I'll quickly try and do that Vivado demo again. It shows the different. It shows something. It's easy to do. It's not as difficult as we think. Like anything, selecting the FPGA, we have to select the right ADC and DAC characteristics. We have to think about the right frequency planning and such like. But actually, you can have a lot of fun with just the small XADC and PWM and delta sigma DACs and such like that are on the smaller FPGAs. So while you all think of questions, I'm going to quickly try and just get this last Hackster project to come up again and see if that wants to. Let's just plug that in and see if this wants to play this time round. If not, I'll have to restart my machine yet again, and then I will add it to the. I'll add it to the video that gets replayed. Doesn't seem like it wants to play too much. I wonder if I add in if I use a different thing, if it will want to do that. Let's try this way. It's all going a bit bonkers. Is it going to play? Or has it all decided to lock itself up? So FFT on the AD3. I presume by AD3 you mean the PMOD AD3. Is that right? Oh, sorry, you're talking about this one, the analog discovery free. Sorry, the analog discovery free. Yeah, no, the FFT is actually quite good. It'll go out to a couple of meg, I think. So you can take it a little bit further than that. I quite like the. I was actually going to use a different oscilloscope, but then I realized I couldn't. For some reason, the software wouldn't run to put it on my machine. So if we run this demo application, which is the application that's running on the for the XADC, so it's going to download into the tool. It's going to start doing some processing. Hopefully it's going to program the device and then start running. Everything's much slower when you're sharing your screen. So this uses a RISC-V microblaze to run through it, and I will, like I say, this project will be up on Hackster in a little while because it's actually quite a cool project for showing how to work with signals and interfaces and such like. So now that project's running, I should be able to come over here and do conda activate, show that I can't type while I'm doing this. And then if I do Python here we go. So this is an application that's running on the board, and it's sending data back. As you can see at the moment, the XADC's writing out some really crazy value for the temperature because it needs a supply voltage. No, it needs a supply voltage applying to it to actually bias the RC. But once you get that, that'll come, and it'll come in close to what the other temperature is. And if we just hold, if I just hold this and change the value of it, we should see again. So as I increase the temperature, we see the XADC. It's measuring the it's changing and measuring the values. And if you want to take a look at the values in Vivado, you can refresh the device, hopefully, because I put an ILA in there, and you can trigger and see what's coming in out of the XADC. So this is the XADC value here, and this TID is the ID. We're not actually using it, but it's the ID channel for the VPVN measurement that's being pulled through and brought through. So it makes it really nice, really simple, really easy to use on the XADCs and get your system sort of up and running. So if with that, I have about 5 minutes we have a couple of minutes to spare maybe. So if anybody's got any other questions, I would love to try and answer them. If not, I would also ask another question. Obviously, we're getting to the back end of this year now, so I'm not going to be running any more webinars this year, but we will be running some webinars in 2025. So if you've got any subjects, any topics that you particularly want to see covered, just drop them in the chat, or drop me an email, or mention it to me on LinkedIn or Twitter or wherever you follow me, and let me know what you would like to think about. I'm thinking about some based around security, some based around sort of verification. How to do basic verification of the design, and I'm thinking we did a timing one this year. I'm thinking about doing a more advanced timing one also. So any thoughts, any things? Oh, we're going to do an image. I'm going to do an application-based one as well. So we're going to do a live build at some point of an image processing system. So we're going to build an image processing system. We're going to get a camera. We're going to build an image processing pipeline. We're going to write some image processing. We're going to write some software, and we're going to get an output display, pretty much like what's shown on the displays behind. But honestly, any thoughts, any questions for next year's webinars would be greatly appreciated. UVM, yeah, UVM is interesting. So I try to keep it to like what Vivado can support. And I think Vivado can support quite a lot of UVM type UVM. I'll have to go away and double check, but I think it can do that. Oh, I like the Vitis hardware acceleration idea. We did that a couple of years ago, and do that. Martin, maybe in answer to your question, maybe. This one's actually sponsored by AMD, so I'll be non-committal on that because AMD have been very good to us over the years to support these sort of things. So I'm going to take a note of those things. So Vitis hardware Excel, verification on UVM. Yeah, anything that anybody's got. AIE use cases. I like that. The AIE is really interesting. We did some we did some blogs on it recently using Model Composer. You can do some really interesting things outside of just machine learning edge AI using those AIEs. You can do some really cool things with FFTs and such like in them. So that's a great example. Any other Vitis HLS? We did one on Vitis HLS not long ago, but actually that was before Vitis Unified came in. So we could take perhaps it's about time to take a look at the entire accelerated flow, Vitis flow again. Is there any applications that people might any applications are there? I will put it on there. So I think I'm A Taylor FPGA. I can't remember if I'm A Taylor FPGA or Adam Taylor FPGA, but you can find me with the same name on X and on Blue Skies as well. I think it's Blue Skies. You know, the new one where everybody is. But I'm most active on LinkedIn, so that's the best way to kind of follow all the information. Okay, Jimmy, I like that one. How to reduce resources. That's a good idea. So yeah. So anything that anybody's got, you know, any thoughts, any projects, you know, just bang them across. Let me know, and we can take it from there. Image filters, yeah, image filters. We can do that. So my plan actually is to create an initial image processing platform using something like probably an Artix or a Kintex device that just takes an input from the HDMI camera, you know, like a little like GoPro type thing, and then outputs it on HDMI display as fast as possible. So, you know, minimum latency, no frame buffers, no nothing like that. And then actually my plan is to go back and then look at things such as Vitis Model Composer and the Vitis HLS vision libraries and show how you can then drop in the middle image processing filters on that live video stream. So, for example, to be able to do, you know, just Harris edge detection or things like that. RF sock. We have some RF socks, so I will do that. Algorithm flow related, for example, PID. Yeah, we could do like PID. PID and scripting. Scripting is always one. I actually did write a blog on how to do the pink, how to do Vitus, Python scripting with Vitus Unified IDE. PID is a good one, actually. It's used in so many different applications. So yeah, anyway, we're on the hour, so I'm sure everybody's got to go and do some work because it's I've taken up enough of your time. So you can use pink on the Z board. You can. You would have to create your own pink image for the Z board. So basically, anything with an A9 or an A53, you can build pink to run on it. But you would have to build your own pink image. It's really simple. There are some instructions on my Hackster showing how to do it, and I've done it for, like, for example, the Cora board, the Mini, the Micro Z, the Snickerdoodle. I think that's it. But yeah, we've done it for many different types of boards, so you can do it, and it's not difficult to do it, but it takes a while for the compilation, shall we say. And I would recommend you do it on a virtual machine, not a machine, just in case anything goes wrong. But you can do it on Pink. And if you want to know more about Pink, there is a webinar on Pink available via our website that we did maybe last year, where we talk about Pink and how you can use Pink. That I really like, so I'm going to wrap it up now. Thank you very much for coming. Sorry about the little Vivado difficulties in the middle, but hey, we're FPGA engineers, and that's what we spend our lives doing, is fighting and battling tools. So I will wrap it up. I will say thank you very much for attending. And yeah, next year, keep an eye out. We'll run another series of webinars, probably starting towards the back end of January or beginning of February time, because these are great. These are great fun. I enjoy doing these. I enjoy creating the demos and everything. So thank you very much, and have a great day, great evening, great weekend. And yeah, thank you very much. Bye bye.